we've learned that two charged objects can exert forces on each other, forces known as electrostatic forces. In fact, this force shapes nearly everything around us. The electrostatic force between electrons and protons holds atoms and molecules together and plays a key role in chemical bonds and molecular structures. But centuries ago, this force was still a mystery. In the late 1700s, a French engineer and physicist named Charles-Augustin de Coulomb took the first major step toward understanding this force. He conducted meticulous experiments to measure the forces between charged metal spheres. Through this work, he established a law that would become a cornerstone of electromagnetism, a law that is named in his honor. Coulomb used a sensitive instrument called the torsion balance to measure force. It consists of a horizontal bar, suspended by a thin wire, with two spheres attached at its ends. One of them is charged, and the other acts as a counterweight to keep the bar horizontal. When another charged sphere is brought near the suspended sphere, the electrostatic force causes the bar to rotate, twisting the wire. The force can be found by measuring the amount of twist in the wire. To study the effect of distance on the force between charges, he carefully varied the distance between the two charged spheres. He first measured the force for distance r. When he doubled the distance, the force reduced to 1/4. When he tripled the distance, the force dropped to 1/9. He saw a clear pattern emerging between force and distance. This led him to conclude that the force is inversely proportional to the square of the distance between the charges. Next, he wanted to study the effect of charge on the force. But here, he faced a major challenge. At the time, there was no reliable way to measure the amount of charge on an object. Back then, static electricity was commonly generated by rubbing different materials. Rubbing longer would build up more charge, but there was no way to increase it by exact amounts. Similarly, they could transfer charge by contact, but again, not in precise amounts. This was different from distance. Distance could be measured and adjusted accurately, so he could adjust it exactly as needed for every trial. But how do you study the relationship between force and charge if you can't measure charge? Coulomb got a brilliant idea. Instead of trying to measure the exact amount of charge, he worked with relative values. For example, take a charged metal sphere. Now take another identical sphere that has no charge and touch it to the charged one. Some of the charge flows from one to the other. And because the two spheres are identical, the charge gets evenly shared. After separating them, each ends up with the same amount of charge. We may not know the exact value, but we can say that both sphere A and sphere B now have the same amount of charge. Let's call it Q. By repeating this process, we can get spheres with charge Q by 2. Using this method, Coulomb created different combinations of spheres with known relative charges. He then used these charge combinations to study the effect of charge on the force between the spheres. He first measured the force when both spheres had a charge of Q. Then he used spheres with charge Q by 2. This time, the force dropped to 1/4. Next, he used spheres with charges Q by 2 and Q by 4. Now, the force dropped to 1/8. He saw a clear pattern emerging. The force depended on the product of the charges on the spheres. These observations led him to formulate what we now call Coulomb's law. Let there be two charged bodies with charge Q1 and Q2, separated by a distance r. The charged bodies can be considered as point charge if the size of the charged bodies are very small in comparison to the distance between them. Q1 and Q2 repel each other if both Q1 and Q2 are positive or if both are negative. They attract each other if they are oppositely charged. Coulomb's law helps in determining this force of attraction or repulsion between two charges. According to Coulomb's law, the magnitude of the electrostatic force between 2 point charges at rest is directly proportional to the product of the magnitude of charges and inversely proportional to the square of the distance between them. This force acts along the line joining the two charges. Let's look at the mathematical term. We introduce a proportionality constant to get an equation for the force. On rearranging the equation, we get an equation for the constant. The value of this constant can be determined experimentally by measuring force between charges using precise instruments such as a torsion balance. For example, force between two charges of 1 microcoulomb each, separated by a distance of 0.1 meter in air or vacuum, is found to be 0.9 Newton. If we use these values in the equation, we get 9 multiplied by 10 to the power of 9 Newton meters squared per Coulomb squared. This is called the Coulomb's constant, and it is denoted by letter K. If the experiment is conducted for the same two charges, separated by same distance but the medium between them is changed, then the force also changes. As a result, value of the constant also changes. This implies that the value of the constant in the Coulomb's equation depends on the property of the medium. This property of the medium is called the permittivity. It turns out that the constant of proportionality in Coulomb's law is equal to 1 over 4 pi epsilon, where epsilon is the permittivity of the medium between the charges. Here is a list of different mediums along with their permittivity. The permittivity of vacuum is called the permittivity of free space. Therefore, for charges in vacuum, the constant in Coulomb's law is equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Why does the medium affect the force between charges? And what exactly is permittivity? To truly understand that, we'll need to explore a few more concepts, like electric polarization, dielectric materials, and the internal behavior of materials in an electric field. We will get there step by step and it'll all start to connect.